Alright, so just sent the link out to my second and fourth blocks with what's on the quest. I'm going to get started with that in a minute. Actually get people to tune in. I know juniors have had a lot going on this week. You probably forgot there was even a quest tomorrow. So tune in now and we'll just go over what's on this thing. Okay. I'll just fix it anyway. Okay. Alright, so, quest tomorrow. Quest tomorrow. What is on it? Alright, so, let's get started. So tomorrow's the quest on nuclear chemistry. And I just wanted to go over what was on it, just give you guys a little refresher of what we did the past few days. It's a very, very fast unit. And so, we'll start with what we started with, which was half-life. That's on there. And half-life is a unit of time. So you think half-life, you think time divide by 2. So it's time 2 divide by 2. So, if you're not given a half-life, more likely than not, you're going to have to look it up on table N. So when you go to table N, right next to each nuclide, gold, carbon, calcium, etc., is the half-life. So as you go down, like gold is 2.7 days, carbon is 57 years, calcium is 182 milliseconds. All of these things have different half-lives. Some very long, years, some very short, seconds, some extremely long, billions of years. So, regardless of what nuclide you're given, the process to solve them is the same. You always start at 100% of your substance, or fractionally, that's 1 over 1. And after one half-life, you get down to 50%, or 1/2. Go through a second half-life, and you're down to 20%, 25%, or 1/4. And you go through a third half-life, and then you're down to 12.5%, or 1/8. And then you go through a fourth, and you're down to a 16th. And you just keep dividing. Literally all you're doing is constantly dividing by 2. And each one of those steps will take the same amount of time. So whatever atom you're given, it has a specific half-life where X amount of time has to pass. And after that time has passed, it just divides by 2, snaps in half. So let's say you were doing, let's just pick a random one. Hydrogen 3 has a half-life of 12.31 years. So you start with 10 grams of hydrogen 3, which is 100% of hydrogen 3, and then after 12.3 years, you divide by 2. After another 12.3 years, you just keep dividing by 2 every 12.3 years. And how do you know when to stop? When do you stop dividing by 2? The problem's going to give you some sort of hint of when to divide by 2. It might say, how long would it take hydrogen 3 to go through 3 half-lives? And so you would go 1, 2, 3 half-lives, add those years together, you get about 37 years. Or how long would it take for hydrogen 3 to break down to 1/8? How long would it take hydrogen 3 to break down until 1/8 of the original sample remains? Or 1/8 of the unchanged sample remains? Again, just keep dividing by 2 until you get to 1/8. 1, 2, 3. Add up all those years, 12.3 times 3. Again, you get about 37 years. So whatever the problem is, you kind of approach it the same way. So if they give you a mass to start with, let's say you start with, or let's say you're working backwards. Let's say 50 grams remain after 3 half-lives. I keep doing 3. Let's do 5. 50 grams remain after 5 half-lives. What was the original mass? So this one, you got to work backwards. So it said 50 grams is what you end with. You have divided by 2 5 times, and you've ended with 50 grams. Where did you start? So if it tells you you divided by 2 5 times, all you have to do now is work backwards and multiply by 2 5 times. So you can do it simply as you had 50 grams at the end, and literally just times it by 2 5 times. 100, 200, 400, 800, 1600 grams. Or you can do 50 grams times 2 to the 5th, because that's the same as that. But honestly, I think it's just easiest if you just multiply 2, 2, 2, 2, 2, 2, or divide by 2, 2, 2, 2. Instead of using an exponent, because you could put in the exponent wrong, or make a silly mistake, or make it backwards, or do 2 to the 1. Who knows? You can, once exponents get involved, you can make a silly mistake somewhere. Just, if you start with 50 grams, and it went through 5 half-lives, or sorry, if you end with 50 grams, and you went through 5 half-lives, that means you've divided by 2 5 times to get to 50. So then just multiply 50 by 2 5 times to get to where you started. And that's the basic principles of half-life. Take what you start, divide by 2 until you get to where you end. Or take where you end and multiply by 2 until you get to where you start. And your quest tomorrow is about 26 questions. It's a quick 26. A lot of it you can use your reference table for. Yeah, I'll do like one more type of half-life problem. How much iodine 1/3? Let me pick another one. Let's do K42 remains after 80 years. I have no idea what its half-life is, but we're about to look up. So, K42, how much remains after 80 years? You don't know what its half-life is, so you need to look it up. If I go to the reference table, find K42, I'm going to change this probably to hours. Which will be divided by 2 for a while. Its half-life is 12.36 hours. Alright? So, in 12 hours, K42 will divide by 2 and become half every about 12.36 hours. So, I'm going to pick a different number than 80 years, because that's a little bit too much. And I'm going to do 49 hours. Do I want to do 49 hours? Let me see. Yeah, 49 hours. Because 80 years will be dividing by 2 forever. So let's say 49 hours. So we said one half-life was about 12.36 hours, right? 12.36. I'm like all over the place. Yeah, 12.36 hours is one half-life for K42. So I have to divide by 2 until I hit 49 hours. And to figure out, well, how many times do you have to divide by 2? If you do 49 divided by 12.36, you'll get about 4. So, if you know 49 hours is given in the problem, and you know one of the half-lives is 12.36 hours, it's about 4 half-lives in this question. You can also set up a proportion where if one half-life is 12.36 hours, how many half-lives is 49 hours? Multiply and divide, and again, you'll get 4 half-lives. So I have to divide by 2 4 times. So how much K42 remains after 49 hours? So they didn't give you a starting mass, so you start 100% or 1 over 1. And you have to divide this by 2 4 times. Three half-lives. And then finally, after the 4th half-life, you divided it by 2 4 times 1/16 / 66.25%. How do I know to express it fractionally or as a percent? It'll tell you. It'll tell you in the problem. It'll say, please express this as a fraction, or please express this as a percent. So that's half-life. It's literally, all you're doing is dividing by 2. All you're doing is dividing by 2 in a certain amount of time. Okay, a big portion of this is natural transmutations. So what's a transmutation? Because you're going to see that word pop up. A transmutation is when an atom changes into a totally different atom. So like a carbon atom changes into a nitrogen atom. Now, when you see a reaction, a nuclear reaction with one reactant, so one thing on the left side of the arrow, this is a natural reaction. Therefore, it is spontaneous. And since it's spontaneous, it happens without any outside influence. Carbon-14 will break down like this naturally. And it breaks down like this because carbon-14 is unstable. And since carbon-14 is unstable, it will break down every, according to table N, like 5,700 years. Release a particle over here, this is called a beta particle, and break down into a nitrogen. Alright, so that's a natural transmutation. And there's 4 types that you'll see of natural transmutations. There's 3 types on table N, and it's under this column called decay mode. Alright, so we got B-, B+, and an A. And if you're like, what the heck does that mean? You scroll up to table O, scroll down to table O, and all those symbols are listed and defined with their charges and their names. So, the A is an alpha particle. The B- is a beta particle, the Y is a gamma particle, and the B+ is called a positron particle. Now when you look at these, this top number here is the mass, and this bottom number here is the charge. So most of these have a positive charge or no charge, where beta is the only one with the negative charge. So beta's negative, alpha's positive, gamma has no charge, neutron has no charge, proton has a charge of 1, and beta has a positron has a charge of 1. And the biggest thing you're going to need to be able to do with these is predict using table N. So you got to use table N. It'll say like which one of these is positron decay. So if you see that, you got to use table O. You might need to use a combination of these 2 tables. So it'll give you a list of particles and asks what's the decay mode in these particles. So that one you need to use table N. And then when they give you the symbols on table N, you might need to look up what they stand for on table O. So you need to use a combination of these 2 tables. The biggest one you're going to need to do is be able to predict a missing product when given a certain reaction. So what does that mean? I'm gonna make up problems here. So let's say you had an element X that had an atomic weight of 30 and an atomic mass of 80. And you look up element X on periodic table, or sorry, on table N, and it releases an alpha particle. In a reaction, charge, mass, energy is conserved in any reaction. So here, these numbers need to stay the same on both sides, and up top, these numbers need to stay the same on both sides. And if they're not the same, then we need to balance this. So what's missing on the right side? So here we have a 30. There's a 2. What plus 2 is 30? 28 is 30. 28 decays into element Y, or 28 is whatever Y is. And then the mass, it's 80 over here. It's 4 on the other side of the arrow. What plus 4 is 80? 76 is. Now when you finish this problem, especially if it's not multiple choice, go to the periodic table and look up what is atomic number 28. Who is Y? If its atomic number is 28. It's a little tedious, but you go to the periodic table and you discover that atomic number 28 is nickel. So when it asks you to fill in the blank here, make sure you don't write Y. Make sure you write nickel 2876. Now a real problem will also not give you X. It'll give you whatever element it should be. But when you're doing these, especially on short answer questions, don't just put like X 2876. Who is 28? You have to be specific. Let's do another example with X here. But I wanted to release a beta particle this time, because sometimes people get a little confused with beta. Now let's do the easy one. That's 80. That's 0. So this top number has to be 80 again. So the mass is 80 on both sides. That's 30. That's -1. So it's very tempting for students to put 29. But 29 minus 1 is not 30. 31 minus 1 is 30. Alright, so be careful with beta. Number 31 on the periodic table is gallium. 31 gallium. So your final answer would be 3180 gallium. Alright. That's a big chunk of it. Penetrating power is a word that will come up for sure in this quest. And least to greatest, you have to know both ways. It's just alphabetical order. Least to greatest is alphabetical order. Alpha, beta, gamma. So basically what this means is gamma rays can penetrate through various materials, like meaning pass through them. I think the only way one of the ways at least that they prevent this or help prevent humans from gamma radiation is wearing lead suits. So it's pretty powerful. Versus alpha is weaker, doesn't pass through as many materials as gamma. And beta is in the middle. So it's alphabetical order. Alpha, beta, gamma. You need to know attraction. So in this case, it's just opposites attract. So alpha and positron are attracted to a negative charge. A negative charge. Because alpha and positron are positive. Beta likes positive charges. Again, opposites attract. So beta, since it's a negatively charged particle, will be attracted to a positive charge. And gamma likes no one. Because gamma is not charged. so it doesn't experience that electrostatic attraction. And I believe that's it for natural transmutations. What is artificial transmutations? So artificial means it doesn't happen naturally. There's some outside influence. And an artificial will always have two reactants making multiple products. With the key being, there's two things on the left-hand side of the arrow. So if you see two things on the left-hand side of the arrow, it's artificial. Which means it's not spontaneous, because we are influencing this. We are causing this to happen. This doesn't happen naturally. We're doing it in some way, shape, or form. So it's not spontaneous. It's still unstable. And there's two main types. There's fission, where in fission, we will always take some neutron particle and fire it at a big atom. Usually, it's almost always uranium. And whatever uranium weighs. And then when you do that, uranium is going to break down into X plus Y, and then usually it releases like 3 other neutrons or something like that, where X plus Y have to add up to 92. So, let's just say 60 and 32. And then these have to add up to 291, because we have 1 and 290. There's 3 of these, so that weighs a total of 3. Don't forget that, because there's 3 of them. So if that's 291, that's 3. These two combined must weigh 288. And main thing being here with fission is you have 2 reactants on the left, and then the big element, the big atom, is splitting into 2 smaller ones. Atom splits, converted to a lot of energy. Like, think nuclear bombs. Big amounts of energy. Fission releases a lot of energy. A lot. Alright, and this is artificial. And then there's fusion. In fusion, 2 atoms will fuse and become 1 atom. And 9 times out of 10, it's a helium atom. So usually they give you, majority of the time, they take 2 hydrogens and then fuse them together to make a helium. And then it releases sometimes. Sometimes it'll release something else. Yeah, that's fusion. Again, mass is getting converted to lots of energy. Lots of energy. And that's fusion. So those are the 2 unnatural ones. And they're unnatural because they have 2 reactants. There's always 2 things on the left-hand side of the equation when you have an artificial, unnatural nuclear reaction. The only other thing that's really on here is, knowing those 4 nuclear particles that have benefits. So there's I-131, I for thigh. When you see iodine-131, you think thyroid. It helps treat thyroid disorders. There's cobalt-60, O for cancer. When you see cobalt-60, you think, oh, this helps treat cancer-related disorders. There's carbon-14, which dates, aka tells you the age of organic matter. And all that means is it tells you how old once living things were. Or currently alive things. But usually it's on, they'll use in, fossils and stuff. So that dates formerly living things. And then there's uranium-238, something like that, which dates inorganic, aka geological, aka rocks. Stuff like that. Stuff that was never alive and never will be alive. Knowing like the general idea of what's bad about nuclear waste, you know, it creates harmful waste. So let me start from the top here. What's bad about nuclear energy? You can create harmful wastes. These things have long half-lives, so they're hard to get rid of because they stick around. You know, there's that whole nuclear radiation thing. Where do we store this stuff? Stuff like that. So like nuclear waste, nuclear energy is fine, but if mismanaged, it can create issues because there can be radiation and it creates a lot of harmful products, and you just have to be careful. It's a great source of energy, but you just have to be careful. Aside from that, don't forget, if you're given any element, this 40 is the mass, which is the protons plus the neutrons, and that 15 is the atomic number, which is just protons. So if you do 40 minus 15, your neutrons would be 25. Because if that's 15, 15 plus 25 is 40. All right, I'm about to start a Regents review. So, good luck tomorrow. I'll put this on my teacher site as soon as I can. Have a good night.